Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. We are Group 8 from Ordinary Differential Equation course, Monday 7 a.m. The member of Group 8 are me, Muntabihun, Sabita, Rahma, Anugrahaning, and Eli Widianti. In this occasion, we will present about the application of first-order differential equations, especially falling objects with air resistance. A falling object with air resistance. According to Newton's first law of motion, a body will either remain at rest or will continue to move with a constant velocity unless acted upon by an external force. This implies that if the net force or resultant force acting on a body is zero, then acceleration of the body is zero. According to Newton's second law of motion, the net force on a body is proportional to its acceleration, provided the net force acting on the body is not zero. That is, if F is not equal to zero, is net force, M is the mass of the body, and A is the acceleration, then F is equal to M times A. Next. In most following body problems, we neglected air resistance. Here, the air resistance on the falling object is assumed to be proportional to its velocity v. If g is the gravitational constant, the downward force F on a falling object of mass m is given by the difference mg minus kv, where k is constant. By Newton's second law of motion, we get F equal to me equal to m times the derivative of v with respect to t. Next, we get the following first-order differential equation: m times derivative of v with respect to t equal to mg minus kv. This is equivalent with the derivative of v with respect to t plus k over m times v is equal to g. Next is the example. Example 1. An object of mass m is dropped from a hovering helicopter. Find its velocity as a function of time t, assuming that the air resistance is proportional to the velocity of the object. Next, solution. The velocity v satisfies equation 2. So we get the derivative of v with respect to t plus kv over m is equal to g, where g is the gravitational constant and k is the constant of proportionality. Letting p equal to k over m, we can separate variables to obtain dv over dt is equal to g minus bv. Integrate. This is equivalent to dv over g minus bv equal to dt. And integrate both sides, we get integral of 1 over g minus bv dv equal to integral dt. We get minus 1 over t, 1 absolute value of g minus bv equal to t plus constant. And this equivalent with 1 the absolute value of g minus bv equal to minus bt minus bc. And then we get g minus bv is equal to the exponential of minus bt minus bc1. Since minus exponential of minus bc1 is constant, then we get g minus bv is equal to c e minus c exponential minus bt. because the object was dropped v equal to 0 when t equal to 0, then g equal to 0, and it follows that minus bv equal to minus g plus c exponential of minus pt. So we get v is equal to g plus c exponential minus pt over v is equal to m over k times g plus c exponential minus pt. The next will be presented by Sabita.
Thank you, Bihun. Next, in the skydiving, once the skydiver jumps from an airplane, there are two forces that determine his motion. First, the pull of the Earth, gravity acting downward, and the opposing force of air resistance acting upward. At high speeds, the strength of the air resistance force or the drag force is proportional to the square of velocity. velocity, so the upward resistance force due to the air resistance can be expressed as F air resistance equals K times V square, where V is the speed with which the skydiver descends and K is the proportionality constant determined by such factors as the diver's cross-sectional area and the viscosity of the air. Once, once the parachute opens, the descent speed decreases greatly, and the strength of the air resistance force is given by K times V. Okay, next. By Newton's second law, F net equals m times a. Since the acceleration is the time derivative of the velocity, this law can be expressed in the form F net equals m times the derivative of v with respect to t. In the case of skydiver initially falling without the parachute, the drag force is F drag equals k times v square, and the equation of motion becomes mg times mg sub minus k times v square equals m times the derivative of v with respect to t. More simply, the derivative of v with respect to t equals g minus b times v square, where b equals k over m. The letter G denotes the value of gravitational acceleration, and mg is the force due to gravity acting on the mass m, that is mg is its weight. Near the surface of the Earth, G is approximately 9.8 meter over a square. Once the skydivers descent speeds reach f equals the root of mg over k meter over second. The preceding equation says the derivative of v with respect to t equals 0, that is, v stays constant. This occurs when the speed is low enough for the weight of the skydiver to balance the force of air resistance, the net force, and the acceleration reach 0. Again, this constant descent velocity is known as the terminal velocity. For the skydiver falling with a parachute, the value of the proportionality constant K in the equation F resistance equal K times V is approximately 110 kilogram per second. Therefore, if the skydiver has total mass of 70 kilogram, the terminal velocity with parachute open is only V terminal with parachute of equals m times g over k over big K equals 770 times 90 over 110 equals 6.2 meter per second, which is about 14 miles per hour, since it is safer to land on the ground while falling at a rate of 14 miles per hour rather than at 120 miles per hour. Skydiver use parachute. After a free next will be explained by Eli.
Okay, Sabita, thank you. For the example 2, after a free-falling skydiver of mass m reaches a constant velocity v1, his parachute opened, and the resulting air resistance force has strength kV. Derive an equation for the speed of the skydiver at t seconds after the parachute opened. Next. For the solution, once the parachute opens, the equation of motion is obtained derivative of v with respect to t equal to g minus bv, where b is equal to k over m. The parameter that will arise from the solution of this first order differential equation will be determined by the initial condition v0 equal to v1. Since the skydiver's velocity is v1 at the moment of the parachute open, and the clock is reset to t equal to 0 at this instant. This differential separable equation is solved as follows. Next. Derivative of b with respect to g over g minus bv equal to integral of dt. Integral 1 over b ln g minus bv equal to t plus e prime. Ln g minus bv equal to minus b times t plus e prime. So we get g minus bv equal to c multiple e power minus bt. Now, since v0 equal to v1, so we get g minus b v1 equal to c. The desired equation for the skydiver's speed at the second after parachute open is next. G minus bv equal to g minus bv times 2e power minus bt. bv equal to g minus, in the bracket, g minus bv times 2e power minus bt. So we get v equal to g over b, absolute value of 1 minus, in the bracket, 1 minus b over g times v1 times e power minus bt. So v equal to mg over k, the absolute value of 1, plus, in the bracket, k over mg times v1 minus 1 times 2 e power minus k over mt. Note that as the time passes as t increases, the term of e power minus k over mt goes to 0. So the parachute speed v slow to mg over k, which is the terminal speed with the parachute open. Next. Okay, I think that's all the presentation from our group. I'm sorry for the mistake and thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.